All right, so welcome everyone to the Student Cluster Competition webinar on the AI benchmarking component that we're kicking off this year. So this is to give you an overview of, the differences of, how AI benchmarking is compared to standard simulation and modeling, to introduce MLPerf. We're really excited to have Vijay Reddy here from ML Commons and from Harvard University. And so with that, I'll let you inform us all on MLPerf and the community.
Awesome, thank you. Great to be here, folks, and I'm super excited about this competition for the students. I think it's an exciting opportunity because ML and AI are sort of here to stay. So understanding how we actually build systems that run these things well is going to be extremely important. So let me start off by talking about what's the key goal. So obviously we're here first and foremost to help you understand about, how we're actually thinking about ML system performance at large, and that's going to tie into the SC competition. One of the reasons, obviously, for having this competition is because AI and ML is something that is going to be pervasive, right? It's going to touch every single aspect of any application that we touch on in the future. So making sure it runs really well is going to be extremely important. And what I'm going to try and do in this talk today is going to be try and teach you how real-world ML systems kind of work in practice. Specifically on the ML aspect, not so much on the end-to-end application level perspective. I'll talk about some of those things in a bit more detail, because then you'll understand how we compare systems and ensure that ML is actually working well. And in the context of the competition itself, we won't be looking at a whole slew of different applications that ML generally supports. Instead, we're going to pick something very specific to look at, which is a RetinaNet model, which is one of the state-of-the-art networks out there in the field, which is used widely for object detection. All right. With that said, the key thing here today is going to be centered around 7 questions for the day. So first, I'm going to talk about what is the state of machine learning today, sort of how we look at machine learning systems. How do we make sense of different machine learning systems? You have an iPhone, you have a Pixel phone, well, like an Android phone, you compare those two things and you tend to understand, oh, well, iPhone has XYZ features. My Pixel phone has all these other features, right? So we have a methodology generally we end up building up when we are actually engineering systems and how to compare different systems. And specifically, I'm going to talk about things in the context of machine learning systems and what are some of the complexities that we get into. And when you want to compare systems, you actually need to have good benchmarks and metrics that allow us to kind of understand things. So I'm going to talk about how do we go about building good systematic workloads that allow us to run them on multiple systems and then be able to make apples to apples comparisons. And then I'll talk about, does doing all that work of kind of creating benchmarks make sense in the real world practice? Like, what do we actually learn from having these benchmarks? And why is it so important to understand what benchmarking or ML is? Now, I'll talk about what does the future hold for in terms of where ML is going and how it's going to influence some of our systems, and then understand, what are some of the things that we might want to scale into in the future. And of course, these kinds of practices, when you have a benchmark, you need organizations to maintain and sustain them. So I want you to understand not just from what you're going to do here and now, rather I'd like you to understand what we are going to be doing as an ecosystem or as a community in order to sustain this, just the way we have GitHub or just the way we have Docker containers and so forth that actually help us build complex systems. We need to understand, how we can create, organizational bodies and tools and mechanisms in order to sustain all this kind of effort that I'll talk about. And finally, I'll talk about what's the final call to action for the community at large in terms of understanding ML systems, and specifically in the context of you, I'll talk about what it means for the student body. All right, with that said, let's just dive in. First and foremost, let's try to understand what is the state of machine learning today as it stands. I would say that, machine learning is very much in the Wright brothers stages. Like, today, when you look at airplanes, you don't think twice about them. You don't think about their safety, nothing. You just kind of hop on them like it's an everyday thing that we do. But if we kind of go back to the time when, the Wright brothers were still trying to engineer these systems, it's pretty remarkable, right? Because if you look at their flight times back in the day, the first flight when they did, close to Christmas in 1903, it lasted 12 seconds and traveled about 120 feet, which blew their mind at that point. They were so excited about it that they spent an hour later working on it and a bit more, and they got 200 feet was a record. Amazing. And a couple of hours later, they knocked it out of the park, but with, lasting for almost 1 minute of flight. And that's pretty epic, right? If you kind of think about it, machine learning is kind of in this phase where like we're seeing this incredible every day, every hour that passes, we see more and more excitement around it. We see it do more and more things, like from sentiment analysis to classifying images, for detecting objects, like, being able to enable like autonomous vehicles and all these different kinds of various use cases that we're seeing. Now it's starting to write code. In the future, it's starting to it's starting already to do amazing artwork and so forth. So very exciting stuff. But still, we're still in the very young ages, because if we go back to the Wright brothers and we look at what happened on that exact same day when all these remarkable things were going on, where they took flight for almost a minute, well, pretty much that afternoon, a gust of wind flipped the machine and it was damaged beyond repair. Really, it was not robust. It was kind of, held by sticks and Band-Aid style kind of thing. But we've come a long way from that, right? Today, if you kind of look at the airplane industry, it's amazing. We manufacture them like they're nothing, given that even though they have like millions and billions of components kind of like all packed together that are all working in perfect orchestration with remarkable reliability. So I would say that we are not here at this point, right? We are very much in the Wright brothers stage. And that's what the state of machine learning today is. Quick stat, I'll tell you. Over $40 billion have been invested in machine learning and AI in the last, say, about 2 years ago. $40 billion. And guess how much of that resulted really in actual fruitful, practical demonstrations of ML in practice outside of all the, the Googles, Microsofts, Metas, and so forth. Turns out about 38 billion of it has zero value that was produced. So there was a lot of money being poured into it because we're all very excited about it, but we're not able to make sense of it in practice, because it's like the Wright brothers states. It's like very much like, bespoke. A handful of people or companies know how to kind of get it somewhat right, but at scale, we don't really know how to make it all work. And so that leads into this question of how do we make sense of these different kind of machine learning systems we'll talk about. I'm going to focus very much on the engineering systems, the computing platforms that support all of this. There's another element of machine learning, which is around data. I won't touch that much on it, but feel free to ask me questions later on. So when we think of machine learning systems, right, a computing system, it's a very complex piece of machinery that we have to orchestrate. At the very lowest levels of the machine, just like any computing system, we have really intricate silicon that we're building, right? And we take all these silicon and we orchestrate it into rich architectures that are then running these, really amazing algorithms that are stitched into or integrated into existing pieces of software. And then we scale these out into thousands and thousands of different computing clusters. And all of that is kind of churning a massive amount of data. So a machine learning system at large is very sophisticated. So the question comes about is like, how do we compare any two machine learning systems, right? And this gets complicated. Now, in reality, there's like a line between the data portion and what's to the left of it. The left side is what I'm going to focus on, which is like the systems aspect. The right side is about the data, which I will not be focusing on today. So if we want to compare any two systems, right, just the way you might compare an Android phone versus an iPhone, you tend to think of what are the cameras and, how many pixel, what's the resolution of the images, how fast does it run, and so forth. Similarly, we want to understand how well our machine learning system's doing. So I'm going to focus everything on the left-hand side. Now, to do this, what you really need is you need to have proper benchmarks. A benchmark is effectively a set of workloads that allow you to make systematic comparisons across multiple solutions, right? So machine learning system A versus machine learning system B, you want to be able to compare them. If you can compare them, then you can make choices. Do I want to get this system or do I want to get that system? If you can do that, it also allows us to measure and track progress. One of the key things about having good milestone markers or workloads that allow us to compare systems is that we can know, okay, over a couple of years, are we making steadfast progress? Because there's lots of nuances, as I'll show you later, that we have to understand to really measure field progress. And if we can do that, then we can effectively challenge ourselves to raise the systems bar, right, and advance the field. So benchmarks are very useful in that sort of sense. Benchmarks have existed for a long time. You have things like LinPack in the HPC community. You have things like spec CPU and for general purpose microprocessors. And for ML, today we're going to learn about what is an ML benchmark, which is what MLPerf does. In order to build a good benchmark, you need to have a rigorous methodology. You really need to understand what you're doing when you're building a benchmark, because it's like a scientific instrument, right? You want to peer deep into the cell where you've got to have the right microscope. Otherwise, you'll come to the wrong conclusions because it's not what you're looking at. It's really the artifact of what you're looking at, right? Same thing. If you want to look into the universe, well, you can stand on, at your house and look up and you won't really see much, or you can put the Hubble telescope and really peer deep into the universes. So you need to have really good methodology, infrastructure, tools, and so forth in order to systematically understand, how systems are performing. And you need to have a really good community that gets behind these sets of workloads that will allow you to do apples to apples comparisons. And that community support is critical when you want good established methods to compare, because everybody has to buy in. Because if any two people say like, okay, I don't agree with your metrics, then, well, then you've got no agreement there, which means that then no one's going to want to use it. So if you want to build a good benchmark, you really have to have good community support. If you can achieve that, in other words, if you have a good mechanism or good benchmark, then it provides incredible value for the ecosystem, because you standardize on a set of use cases and workloads. That's like you and me understanding each other right now because we're speaking English, right? So you understand English, I speak English, we're both speaking the same language. That standardization allows us to, achieve monumental things. And if you have that standardization, then you can compare different things. You can say, okay, I'm communicating a message. You might say, well, I like the way he's communicating, or he doesn't like, you don't like the way I'm communicating. It allows comparability. And we all speak differently, right? So that's a heterogeneous aspect that you tend to see in systems. Systems are also very different. So you want to be able to compare them. And if you have a good benchmark, you can do very complex characterization of the system's capabilities, its power, its performance, its scalability, and so forth. And ultimately, one of the key things that's extremely important in machine learning is that we got to be able to reproduce results. One of the interesting facts you'll find in machine learning or AI is that like only 1 in about 10 papers or so is in fact reproducible. That's because we don't have good standard metrics and definitions of exactly what we want to measure, how we want to measure it, and so forth. And that's really what we want to address. Why? Well, that's because machine learning is very complicated at large. Here, what I'm showing you is the computational requirements on x-axis and the accuracy that a model has, whether it's a cat versus a dog, how precisely is it able to say. And you can see that, in the spread of different, in the scatter plot, you can see many different types of networks that are there, right? Which means that depending on a particular use case, one might choose any particular network. These are all image classification models, being able to say a cat versus a dog. But depending on how much compute you're wanting to invest, you can get very high accuracy, or you can get very low accuracy, right? It makes no sense to say that, okay, I can run 10 times as fast as you, but I'm going to be wrong 50% of the time when I'm telling you if it's a cat or a dog, right? In machine learning, it's all about accuracy. If you say it's a cat, you better pray and hope that it's really a cat, because if you're trying to predict a cancer tumor or something in an image that you see, you want to be as accurate as possible, because you don't want the doctor to come back and say, oh, sorry, my machine learning algorithm was broken 5 years ago, so you're going to die tomorrow. So you got to be very careful about that, right? So because of this rich heterogeneity of options you have, when someone talks about, hey, I ran image classification on a system, it can get very complicated unless you know the exact model and the characteristics of it. Moreover, these systems are very complicated in how we run them. You have many different applications at the top. You have many different hardware deployments. You have CPUs, GPUs, specialized neural processing units, digital signal processors, FPGAs, custom accelerators that support sparsity, don't support sparsity, and all kinds of, shenanigans at the lowest level of the stack in order to get that extreme efficiency. And also in the middle, what you have is like that software from an application level. In order to get to the actual hardware at the lowest level, there's an extremely rich options in terms of what software you want to pick. And the software stack that you pick has implications in terms of what optimizations are performed, right? So if you really want to do apples to apples comparisons of, say, hey, I have a machine learning system X and I'm comparing it with system Y, then it gets very complicated, because you have to understand all these subtle kind of nuance. What task are you running? Are you doing classification or detection or not? What model are you running? What data set are you actually using it? Because that accuracy is dependent upon the data set as well. And what kind of optimizations do you? Lots of nuances. I'll talk about all these in greater detail. So comparing ML systems is very hard, right? So how do we go about building a good benchmark that allows us to do that apples to apples comparisons rather than apples and oranges comparisons, where someone says, oh, I'm better, but you're like, well, I'm not really comparing against the same set of metrics with you, so how can you say you're better? So how do we go about doing that? Well, this goes back to the methodologies that I mentioned, where you really want to be able to bring the community together. Bringing the community together is very critical when you want to have a standard sort of benchmark, because you need everybody to agree on what are the key set of metrics that you can align on, and what are the key set of workloads you want to run, so that everybody can say, okay, we'll all run this particular set of workloads so that we get, fair and representative comparisons. And the way you do this is not by like kind of, sitting in my lab, for instance, and just kind of tossing overboard a set of workloads and say, hey, everybody should use this. It doesn't work because you need shared mindset. To this end, like, what we had to do in order to build such a benchmark was to bring a large amount of the community together and actually get their input and then create a set of workloads that go into AKA MLPerf. MLPerf is basically measuring machine learning system performance based on large public data sets, things like ImageNet and so forth that are available. And then we create benchmarks. We create training benchmarks where we measure how well a machine learning system is able to train a network to say whether it's a cat or a dog. And we build, benchmarks that allow us to measure how well, once you have trained the model, are you able to say whether it's a cat or dog? How fast are you doing it while maintaining your accuracy? To this end, you have to identify, what are the core set of machine learning tasks and models that everybody can agree upon. Everybody's is using AI in many different ways. So getting a shared bit of that mindset is actually tricky, but nonetheless extremely critical. Then you have to understand how machine learning models are actually deployed in the real world. The way machine learning works on an autonomous car is very different from the way it works in your smartphone. And I'll talk more about that later. Then you have to have a clear set of rules, right? Imagine you're at a starting line and someone starts running before, you actually hear the gun sound or the horn sound to say like, start running. Right? Well, that's going to give someone else unfair advantage, right? So you got to have a clear set of rules as to when measurement starts and how measurements are actually going to be done. And then you establish a clear set of metrics. What exactly are you trying to measure? Are you trying to measure accuracy? Are you measuring performance? Are you measuring power, and so forth? And then ultimately, we want to enable the whole ecosystem to move forward. If you want to build systems, generational improvements come about from building repeatable systems, right? So you want to collect the results and publish and make it accessible to everybody so that everybody can look at how are things being done, so everybody can build on prior good work, because that's how we move the industry forward. To that end, the goals of this MLPerf benchmark suite fundamentally are to ensure we get good performance replicability. We pick representative workloads that are, if you measure system performance on it, you actually understand, in the real world, what are the implications of, buying system A. We want to encourage innovation, the challenging, we want to enable people to, push their systems to be better by giving them challenging tasks to work on. We want to enable fair and useful measurement of results so that by measuring something meaningful, we actually get something. Figuring out if a runner's, if he or she drank like, 10 cups of water before is not as useful as knowing, what's the speed of the race, right? Like how fast. So you actually have to measure the proper things. And of course, you want the commercial and research entities, especially like academic institutions, to still take part because they drive a lot of the innovation and creativity. And you want to keep benchmarking affordable. For instance, training machine learning models can take up a huge amount of time and take, almost sometimes 3 months, and they can take an entire data center with thousands of computers. Well, you might not have that in your home or office. So how do you kind of make sure like that gives someone else an unfair advantage? So how do you build a benchmark that enables everybody to take part? So this means that now we've got an interesting problem because machine learning is widely deployed, as I alluded to. There are many different areas. You have classification for vision, you have language tasks, you have audio, commerce, games, and so forth with reinforcement learning. And so since it's so widely used across so many different areas in so many different kinds of, problem tasks, you've got a challenge of how do I pick one out of this, massive list, or one, or, N, and what is that N? Of course, even for a specific task like classification, you might have many different neural network models. Then they might be running on different data sets and so forth, as I alluded to earlier. So you need to have some approach of kind of, going through the space. And the way the MLPerf community kind of goes about it is largely trying to identify, okay, let's all agree together as to what is the definition of a benchmark task. I'll show you one later. I'll talk about like, okay, which benchmark task do we pick? I just said there's so many different areas where machine learning is being used. Do you study all of them? Do you have the time to run all of them? It costs a lot of engineering hours to benchmark systems. So how do you pick a few? What exactly is a measure of performance? Are you going to be happy if you're wrong about cat versus dog, 90% of the time, but you say that, I can do that extremely fast. I don't care. I need accuracy. And so you have the right metric. And of course, systems are very complicated, as I alluded to earlier, that because of the vertical stack is so complicated, sometimes, people are running things a little differently. How do you ensure that, the way things are being run is actually equivalent, independent of some of the quirks that a system will introduce? And of course, when it comes to training and inference, there are lots of different kinds of optimizations that actually affect the end result performance. So you got to make sure, people are staying within some bounds so you can enable apples to apples comparisons. And finally, how do you show your results? All right, so let me kind of dig into some of these aspects. The first and foremost thing is actually understanding what's the definition of a machine learning task. A typical machine learning application includes machine learning components that run like, different kinds of neural network models, but they also include non-ML components. So for instance, like, when you take a picture and on my iPhone, the image looks amazingly beautiful. Well, it's like the reality is it's not what the camera is necessarily seeing. It's what the camera sees. Then there's a raw image that's actually fed into a machine learning model that enhances it with colors and all kinds of stuff. And there's a bit of pre-processing that happens in order to kind of do that work. So that's a total non-ML component that's actually run on the CPU, for instance, before an ML accelerator is actually invoked to run the machine learning task. And then, there might be multiple networks like that you do. And then finally, you might have some post-processing that you do. In the context of MLPerf, the way you will be using the RetinaNet challenge is going to be focused on just one neural network model. So we take one task, like object detection, and we pick one specific model to focus on. Things are much more complicated in the real world, but nonetheless, this is how MLPerf defines it for a very good reason. There's lots of reasons for restricting the scope like this. How are the benchmarks? The next question is like, how do you choose, which network? I said there are so many different networks I can choose, even from image classification. If you remember, I showed you this scatter plot with giant bubbles all over the place. Well, that's basically, image classification, but I can choose AlexNet, which kind of set the whole field into motion. I can choose ResNet. I can choose EfficientNet, which is really good for mobile devices. How do I choose this? Because we're trying to study a real world system characteristics, what we want to do is pick networks that actually are representative. This is one of the reasons you'll be playing around with RetinaNet, because it's sort of cutting edge and it's actually, industry is giving it a lot of interest, but it's not the most bleeding edge network that you will find in the latest state-of-the-art research. It's 10:30. Sorry, that's my computer. You also need to have a rich variety of different networks in a typical benchmark suite. We're only taking one network in this year's inaugural competition. We'll be looking at many more down the road. For now, the point that I'm trying to make here is that typically, networks have very different characteristics. So generally, you want to study more than one network, which we'll expand to in the future. But for now, it's just going to be one network. And the complexity of the networks for a given task can also change. For example, what your neural network is doing on your phone is very different from what your car is doing, because in the car, you have much more higher resolution images, for instance. So you got to make sure that the benchmark captures all these different things. And of course, you got to have a public data set because you got to measure accuracy. At large, just talking about MLPerf, like if I just give you a snapshot of an old suite, for the training benchmark, the details don't matter. Let me emphasize the big items. We try to cover a good range of different kinds of networks. These cover different types of application tasks, like image classification, object detection, machine translation, and so forth. And we use public data sets that are available to everybody so everyone can actually participate. And we provide reference models, right? So you might recognize some things like ResNet, Transformer, BERT, DLRM, and so forth. These are, widely used, well recognized by the industry. And the most important thing I really want to focus here is what we call as a quality target. As I was alluding to, in machine learning systems, the key thing that you really want to get to is the accuracy of quality. How well you do that task. Like, in other words, what does it take for a machine learning system to get to this level of classification accuracy? How long does it take is sort of a critical thing. You might be able to get the system to, reach 10% accuracy very fast, but I don't care. It has to be relatively good enough that I can actually use it in production. So what we actually focus quite a bit on is achieving these accuracy targets. Now, this is if you're training a network from scratch, you will be specifically focused on the inference workload suite. Inference is where the network has already been trained. And in MLPerf, over the past couple of years, we've been evolving these inference networks. So they cover more and more different areas, more different types of tasks, rich number of different kinds of, state-of-the-art models, again, with public data sets. And the thing I want you to focus on here is a quality target. One of the key requirements you'll be given is that your inference system has to meet a minimum quality target, which, for example, in the case of image classification for ResNet 50 is 99% of FP32, which means when you have an FP32, which is a high precision numeric, it gets a certain level of target accuracy that has been trained to. And when you do inference, as I'll show you later, we tend to do some optimizations that tend to drop or negate a little bit of that accuracy. So you're going to see some sort of degradation. So therefore, we say it's 99% off FP32. It gives you a little bit of wiggle room to do some creative optimizations. And we'll only be picking RetinaNet. Again, these are old networks, so you won't necessarily find RetinaNet in here. But the general construct is exactly the same. And so I want to talk a little bit about some of the challenges we typically tend to have in machine learning systems. I'll touch a little bit on training and inference because I want to teach you a little bit about both, but I'll then focus quite specifically on inference for you. So typically when you're training a machine learning system, one of the ways you can look at a system is just kind of look at how fast a chip is able to run, right? Or I can look at how long it takes to actually train the application or the model to the exact task it's supposed to do, right? So what is the complete time it takes to convergence to a certain level of accuracy? Now, the reason you want to be careful about understanding these kinds of nuances and what you're actually measuring is because it's very easy to say throughput can be very high. In other words, I can increase the number of images, for instance, I'm pumping through the system. I can have higher throughput by increasing what's called batch size as a variable in terms of how you feed data into the training system. Or I can use low precision. Low precision means I might do things with int 8 bits, like, just 8 bits instead of 32-bit FP precision. And that low precision means that I can calculate much, much faster because integer arithmetic units run much faster than floating point arithmetic units. And therefore I can get very high throughput. But if you take a step back and you look at the big picture of what it means to get a network to actually converge to meet that 76 or 78% accuracy of classification goal, it turns out that if I do this with low precision, it takes the neural network much, 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 much longer to actually learn because it's low precision. But if I use high precision, which in the lowest level looks like it's actually much slower because the processor is running slower. But if you look at it from an application level standpoint, it actually takes fewer epochs of the amount of time to train. So it's actually better to use what seemingly looks at the microscopic level, high precision arithmetic and lower batch size. It's actually better at the application level because the time to train or the time to get to the solution is much faster. So instead of taking 3 months, you might actually just take 1 month to train. So it's very important to understand these kinds of nuances. A lot of the neural networks also have lots of different parameters that are involved in terms of how they're actually trained. So one of the key things you want to do is there's this notion of hyperparameters that's used in training, and the hyperparameters are kind of like, are supposed to be open. You're supposed to share the hyperparameters with everybody because hyperparameters, you might have accidentally trained the system faster, not because your chip or your system is faster, but because you found the right configuration or the right seed value that actually makes the network train faster. So this is in training. Another thing you'll have is that these machine learning models are inherently stochastic in some cases. So on the left, I'm showing you some network that's achieving a certain accuracy. I think it might be ResNet 50, where you see that no matter what seed, quote unquote, random seeds you're using, which initialize the network, no matter what it is, you always converge at roughly the 60th epoch, which is really nice and steady. In comparison, on the right-hand side, if you change the seed for a different network, you see that one time seed 1 takes maybe about 30 epochs. Another experiment with the exact same seed takes about 45 epochs, and lower is better, right? So the seed configuration you have leads to non-deterministic behavior. So you have to be careful about that and understand these characteristics of the network. Now, switching a little bit more to the inference, which really matters for you. Inference, there are many different scenarios in how are things actually run. So if I take a smartphone, for instance, I have what's called a single stream scenario. What do I measure is what I'm trying to get to. I take a picture and, I do an inference and I get like cat versus dog, right? And so forth. If it's an autonomous car, I have multiple cameras that are located on multiple sides because I've got to be able to see to the front, the left, the right, the back, and so forth. So I'm actually looking at multiple images that are coming in concurrently. Ideally, in a snapshot, at any given point, I have like n number of images coming through because it's synchronous. And then I have to process all of them at the same time. If I'm a server, just like Google or Bing or something like that, it all depends on how the requests are coming in at some arbitrary arrival rates, because we are humans and generating requests at arbitrary times. Then we might have a very different sort of behavior where we don't have a regular sort of cadence as we saw in the previous thing. Or if it's like, your photo sharing app or something like that, like Google Photos, which learns about your faces and so forth, so you can easily search for people, you might just crank all of that offline, when you're sleeping or something like that. So it's like it's an offline scenario. So there are many different ways in which these machine learning models are actually deployed in the field. And this is crucial to understand because there are different metrics that are associated with it. So in the single stream, it's the latency. How long does it take for every single image to come out? If I'm on the phone, I don't care if I can process 10,000 images. Why? Because I only care about when I took a picture, I just want that one picture. I don't care. I'm not taking 10,000 pictures. But if it's a car, I have a latency bounded throughput metric. In other words, I have to process the data in real time because I don't want to run over somebody because I didn't see it fast enough. But at the same time, I got to see all directions, omnidirection, right? So you can imagine there's a latency that's real time in there, but I also have to process the multiple cameras that I have to drive. So that's latency bounded throughput, as we call it. So for servers, there's also a latency aspect. You still want to crunch through a huge number of data, but like there's, an end user has a certain amount of latency, that they can tolerate. And if it's offline, as I was telling you, things are being done at night, I don't care how long it takes, take as long as you want, So it's just throughput down there. So the point that I want you to take away is that in inference, you have to understand which scenario you're looking at, because a scenario has implications in what is getting measured. And you got to understand that because the way you optimize and the way you run the system is going to be sensitive to that. All right, so let's say we built all these benchmarks, and MLPerf, this whole community has built the benchmark, and you are getting one of those benchmarks, like RetinaNet. At the end of the day, we're saying, hey, do this competition. We want you to show, how well these things can run. Is that whole exercise really worth it? And I want to convince you that it's extremely important to do these things by showing you data from the actual MLPerf runs over how things have evolved over the last 4 years, for instance. There's 6 data points here, and each one effectively corresponds to one state-of-the-art result for a network, right? So let's just pick the purple one and forget the rest. But what I want to focus on really here is that you can see from one generation, if I normalize it, the next time that same workload was run, the Resonant 50 was run, it was actually over 4 times faster. The next time it was run, it was like maybe around 10x faster. Then the next, after some more time went, it became nearly 30x faster, right? So you can see that we're getting these ridiculous improvements in performance because now we have a standard baseline that we're comparing against. And this is true of other networks as well. This is in the context of training the networks. But if you look at inference, I'm just picking, just to kind of show you some diversity, MLPerf mobile inference benchmark results for classification, detection, NLP segmentation. And what we're looking at is the throughput, that how fast are we able to crank through. And the whisker plot is showing the distribution of the results. MLPerf is like a competition. Imagine you go into a race and you're competing with yourself, like with others. So the distribution shows you, what are the distribution in times. And you can see at large, generally speaking, from 0.7 to 2.0 version, which is about 6 months or so time gap, you can imagine. We're seeing remarkable improvements in performance because we have this standard benchmark. What this means is the industry is able to start optimizing and working harder and harder to try and make these improvements. Some of these improvements come from taking a system and tuning the software, because that's much easier. And in some cases, there's new hardware that is being built that has been built to actually improve the previous generation. So long story short, yes, all of that work, if you're given a task and you're told to optimize it, is extremely important, because what gets measured gets improved. And benchmarks drive progress, and they also drive transparency. We want to build on really good prior work. And so if we understand how people are actually producing results, then by looking at those results, we can actually build better systems because we can understand the bottlenecks and so forth. So what does the future hold for benchmarking future ML systems? Now I'm starting to pivot a little bit into kind of like the future areas that things are happening, so you get excited about, working on these kinds of things. First and foremost, just talking about inference, right? I talked about, cloud and data center, and I talked a little bit about mobile devices, but the inference ecosystem is amazingly rich, right? Because as I said, ML is going to be deployed all over the place. So for example, it goes from all the way from cloud scale systems like, Microsoft, Google's, Alibaba's, and Bing's, and so forth, all the way down to the tiniest devices where you're saying, okay, Google, or hey, Alexa, and so forth. All of that is ML too, right? They're running totally different networks. And so, which means that across all these different domains, there are really rich and interesting use cases where the different models are doing different things. They're more resource constrained as we go to the left. They're more high performance requirements as you go to the right, and so forth. So what we are touching on today, like in RetinaNet, it's just going to be, it's just the tip of the iceberg. And down the years, you can imagine, there'd be really interesting competitions across this ecosystem. And I also want to tell you about how we actually look at systems. If you take an autonomous car, for instance, an autonomous car is a very complex machine learning pipeline right? It's getting data from different cameras. It's got a LiDAR sensor on top of that. These sensors are generating data that are getting processed by individual networks that are running, for those specific sensors. Like here, the image processing pipeline is looking for traffic lights. It's looking for obstacles. It's doing lane detection, traffic light recognition as to what exactly it is, and so forth. In some cases, you even fuse the data that's coming in from the camera and the LiDAR, right? And so sometimes this fusion is actually done on the CPU and then fed into the accelerator or the ML processor. And sometimes it's done directly inside the ML network itself. And then ultimately, you might do some trajectory predictions. Okay, move left or move right. Oh, in the next 3 seconds, this person is going to be there. So I shouldn't really go there because I'm likely going to hit that person. So it's an incredible pipeline that is running all in real time, right? Similar things when you go into what's actually the next big thing we're all excited about, real time, sort of, augmented reality, mixed reality. These workloads that are running machine learning are actually getting really sophisticated. They're not just running a single network as we are going to study for now. They're actually running multiple networks and they're cascading them and so forth. They're very complex patterns and behaviors, all of which has to run within real-time requirements. And all of this has great implications at the processor level where there's an image coming and you're running it on an accelerator, then you got to display something all in real time, because if you don't display it in real time, you're likely going to have that person actually throw up. In fact, I was just at a keynote before coming up here from Meta, where they were talking about, motion sickness and so forth and how they deal with that in their headsets. Of course, and then increasingly, neural networks are starting to take in multiple sources of input, not just, the user, not just images. It's image plus sound plus text and so forth, or speech and so forth. So they're really rich and really interesting things coming about. Last but not least, if you look at in scientific domains, right, like high performance physics and so forth, these areas are also starting to use ML, and it's what's called fast ML for science. I talked about mobile workloads, I talked about tiny, and I was talking about latencies, that we tend to have, right? And the data rates that they tend to have, like we're taking one picture in mobile device and so forth. If you look at things like jet classification, beam control, where you're looking at trying to control these photon particles that are jetting by in these, large tubes and so forth, where you want them to, hit each other, and you're trying to control their behavior and trying to extract very valuable data that's coming out of them, is extremely challenging because the machine learning systems that we want to build, they have ridiculously tight latencies, absurdly tight latencies as compared to commercial applications. And the amount of data that produced too, there's no way you can offload all this to a massive cloud computing server and do processing. You have to do it at the edge. So lots of very exciting stuff coming about, and it all boils down to how do we build high performance machine learning systems? Because without understanding how we can build those high performance machine learning systems, we're never going to realize the capabilities that we're wanting to with ML. All right, wrapping up. How do we scale and sustain all of this benchmarking sort of an effort? We tend to build, entities like Machine Learning Commons, which I encourage you to check out, where there are multiple companies that come together and support the benchmarks. It's not just companies that come together, it's also academics that come together to share their wisdom. And collectively, because ML is in such a nascent stage, we have to build good benchmarks. We have to build good data sets. We have to establish good practices. In fact, you'll likely be using CK framework that Grigori created, which allows us to very easily run machine learning models, without which it can be very complicated. And the reason for having all of this and trying to onboard you kids to get excited about this space is because, again, ML is still in its right brother stages. And our ultimate goal is that we want to get ML into a production sort of a pipeline facility. And this is going to take, several years, but we need engineers, you guys in the next generation, you're going to have to know how to build and operationalize these things so that we can actually take this ML AI technology for granted and effectively imagine, being able to get on a plane, not even thinking about it, just randomly booking a flight and being able to be 100% sure it's going to get you to your destination. That's the sort of vision that we ultimately all want to get to, right? And it takes an entire community to be able to pull this together, starting with you folks. So what's the call to action here? Hopefully you understand that the reason for having the competition is that AI and ML is extremely important for every single application domain. It's very rich. At the same time, it's very complicated. And therefore, by competing and understanding how to run the workload, you will get a taste for how ML systems work in practice. And that appreciation will open your mind, probably blow your mind, hopefully not literally, in terms of what is actually possible, right? And we're going to start doing that by taking RetinaNet which is one of the state-of-the-art networks, which has really interesting characteristics that I won't get into because it was going to take much longer if I was going to start explaining RetNet itself. Nonetheless, it's a neural network model, and what we really want to do is get you folks to actually, try and work with the system and optimize it. And that's all I got for you, and I'm happy to take any questions. I'm going to turn it back to the organizers.
Thanks, Vijay. That was great. So are there any questions from the students? So I know it's like a fire hose of information because AI can be very different than standard simulation and modeling. So a few things that Vijay touched on was that the competition for this year, the competition model that we'll be using from the MLPerf benchmark suite is RetinaNet, which is object detection. We will be giving additional information on how to run RetinaNet, and it's going to be Inference this week. And also, I don't know if you caught in Steve's announcement, but this is an optional benchmark because we know on Monday you have 3 other benchmarks you're going to be running, but if you take some time to do this, we know the competition can be really fierce. So, even getting a few additional points can be all the difference in winning. So completing this benchmark will give you some additional points to add to your total score. So we see a question here. So just curious, is there any plan for MLPerf to extend to more emerging models such as GNN on billion edge graphs where the bottleneck could be different than the traditional models?
Yeah, so that's an excellent question. The answer is yes. Obviously, GNNs, you're spot on. They are being widely used. They're increasingly becoming commonplace. And so there is definitely that momentum there. That said, it's not clear about when that network will actually become mainstream. Again, it sort of takes a little bit of maturity in the ecosystem where everybody has to say okay, this network has got all the key characteristics that it's representative enough, because GNNs also, there are many different variants of it, but it's definitely in the place. And last but not least, the question that you asked is extremely important, which is how do we keep these kinds of things up to date in MLPerf, right? Because ML is continuously evolving. This is why the community aspect is so important, because the community input like this, you asking, what about GNNs? Why do they know GNNs? Is exactly what leads into improving the benchmarking. That's why in Inference, I intentionally showed improvements in going from 0.5 to 0.7 to 1.0 and so forth. Good question.
So additional questions are more on the logistical side. Yes, so this is benchmarking for Monday. And also, I can't say exactly when we'll get the details. We're trying to get them together today. Grigory and Arjun are on the phone. So I'm going to actually share, let's see. I'm going to share my screen for a second, just so you can kind of see some of the connections, and hopefully you'll take some time while you're waiting for the benchmarks to be released, to the benchmark information to be released, to kind of look around. So all of the benchmarks come from ML Commons, the MLPerf suite. If you take a look, there are a large number of categories of benchmarks here. We're doing the Inference Datacenter, and what MLPerf and ML Commons are working on right now is trying to make these benchmarks more accessible and reproducible through an education and reproducibility effort, which is being led by Grigory and Arjun, who are also on the call. And they're trying to make it easier for us to deploy some of these models, which is why we're waiting for those instructions. And if you want to go ahead and take a look, you can look through the site. There, RetinaNet is up on the site. You could look at the model previous to getting all of the full instructions. And one of the things that we're going to try and work towards, not just getting the additional points for the competition, but you could actually get your system and your team's name on the leaderboard if you would like to submit for the next round of the inference results. So you could be a submitter up here with your system that you're running for STC and list your RetinaNet results from the competition. Not just from the competition, it could be something that you also take home with your teams. And the next leaderboard will be updated in January. So that's also a really exciting thing to get some fame and glory on the website. Grigori.
Hi, can you hear me?
Yes.
Oh yeah, hi. So just to mention that the idea for this student class competition is not to finalize the submission during the competition itself, because it will be quite complex process. The idea for you is just to try to prepare and run the benchmark and get reasonable results. Again, we will release the details hopefully tomorrow. After that, we will be happy to work with all the teams for the next month or so to help them prepare the full submission if they want to. And that's where you can get like the optimized submission for the next round, which will be in February, I think, next year. So just to let you know about that.
Thank you so much. Yeah, so even though for the STC competition, the benchmark running is just during the week of STC, this can definitely be something you continue outside of the competition.